Welcome back. As we mentioned, we are going to look into some options for tuning this high value resistor that we just discussed, and the main motivation is that we want to have some options to compensate for the process and temperature variations. So, we will see in simulation exercise also we have options of doing temperature and process simulations. We can run temperatures and different corner simulation to see how much the resistance varying over a given range of temperature, and in general integrated circuits can be exposed to a wide range of temperature, even if it is for a specific application like a neural interface in this case. And likewise, process point of view also we can have significant shifts in the Vt. It can be time dependent shift as well, which can shift the characteristics. So, we want to have some kind of tuning options which can be used to calibrate these values either automatically or one time. The preferred way may be to have automated calibration, so that once you have deployed the chip for its normal operation, there also you can have some mechanisms of sensing it, and then again using the tuning options for adjusting the values. So, we will not discuss all those, we will just discuss how we can implement one possible scheme for tuning. So, the basic mechanism involved in tuning is that we want to intentionally add a kind of battery over here, with the help of which we can adjust the resistance level that we are going to have. For example, if we ensure a significant voltage drop between the V out and the gate, likewise if we ensure some significant voltage drop between the V in and the gate of the M2, the transistor which is getting on will be getting on more strongly, and likewise the transistor which is getting off will not be staying off that strongly. So, basically if I insert an additional voltage over here such that the transistor staying off has an additional VSG drop, that can help us in reducing the overall resistance across the switch. That is one way through which we can control the overall resistance provided by this device. So, let us just look at one possibility, how can we create such a battery and put it in series with this MOSFET, so that the overall resistance can be reduced, and we can try to simulate that example also and try to see how we can obtain such a control in the device. So, one possible way of implementing such a transistor level battery is to use a tunable current load So, here I have drawn a structure which is generally termed as a pseudo NMOS gate. So, this kind of scheme can be used for implementing digital logic, but here we are using this particular structure to implement a desired voltage drop between the source of this PMOS and the gate of this PMOS, and we are going to use these two terminals as effective battery. Basically, the voltage developed across the source and gate of this PMOS can be used as an effective battery. Basically, we are going to connect this particular source terminal, for example, at the output point, and the gate terminal will be connected to the gate of the MOSFET. So, that as compared to the output point, we are having a VSG drop between this point and the gate of the MOSFET. Likewise, for the other side also we can do the same. We can connect the source terminal of this particular circuit at this point, and the gate of this PMOS can be connected over the gate of M2. So, that as compared to the input point, we are having an effective potential drop between the input and the gate. So, that the potentials arriving at the gate are slightly lower as compared to the potential at this point and the output point. That will basically help us in shifting the resistance towards lower values, because the effective gate potential will be lowered as compared to what we have at the V in and V out. So, the strategy will be that we try to make the resistance for highest possible value, and then have an option for tuning this voltage, so that we can reduce it intentionally. So, the baseline transistor, series transistor, we will try to make it offer very high resistance values while keeping the option for pulling it down. So, by adjusting this potentials, we can try to pull it down. So, let us look at how by tuning some of these switches drawn over here we can tune the VSG. So, as we know, if we have these transistors operating in subthreshold region, suppose these transistors are implementing some kind of current source mirroring a very small current. So, we can ensure mirroring of very small current of the order of say sub nano amperes, such that the total current even summed up with all these 4 transistors is very small flowing through this PMOS. As a result, the VSG developed for this PMOS will be logarithmically dependent upon the current, because we know that if the total current is very small, the VSG will be logarithmically dependent upon the subthreshold current, or in other words the subthreshold current flowing through the MOSFET depends exponentially on the VSG of the MOSFET. As a result, if we are controlling the switches and we are making these transistors binary weighted W, 2W, 4W and 8W, we can program the total current flowing through this bank in a linear fashion, and as a result the VSG can also be controlled in a logarithmic fashion. So, if you are adjusting these switches, so depending upon which switches you are turning on based on a binary 4-bit word, we can control the total amount of current flowing through the PMOS, and as a result the VSG also gets controlled, and hence this logarithmically controlled VSG is going to once again control the resistance almost in a linear fashion. You are going to have a linear range of resistance which you can tune by using the switches over there. So, this is one way in which you can insert a effective battery between these terminals and the gate, and hence control this battery by controlling this tuning options, this switches over here. This in turn controls the effective resistance coming between this V out and V in terminal. So, we will see in simulations also that incorporating these kind of tuning option can help us in obtaining a wide range of resistors values through the use of this control switches. So, this is just another example how to address the practical issues in silicon, how to address the variability and time dependent drifts in the resistance that we are trying to create for our circuit. Any question? Okay, so we can proceed towards the next analysis, which is the frequency response for the differential case. We have just looked at the DC biasing and we tried to arrive at a possible scheme where we are not violating the frequency response, we are not violating the noise constraints, we are also ensuring robust operation by incorporating tuning options. Now, next we are going to look at the differential frequency response. Once again, coming back to our differential amplifier circuit, for the fully differential operation, considering the common mode to be DC, we are ignoring the common mode circuit, and so we are back to our fully differential circuit, and for overall differential gain, we know that from the input to the output we have GM RO whole square gain, and we also need to find out the critical poles in this circuit, which are going to be at the first output nodes, first stage, because here we have an equivalent impedance given by RO by 2. Remember, for the differential mode operation, this point will be AC ground for the differential pair. As a result, these are also acting like the common source amplifiers with current source load. As a result, the impedance over here for the differential operation will be just RO by 2, R up parallel R down, both of them RO, and assuming both of them are close or similar, RO by 2. Likewise, at the output point, anyway they are acting like a common source amplifiers with current source load. As a result, the overall impedance over here is also going to be RO by 2, and we can find out the overall capacitances connected at this point. So, we can look at the overall parasitic capacitances coming at these 2 points, and that is going to give me the final parasitic RC value, and hence from there we can calculate the overall poles for this transistor level circuit. So, we also looked at the feedback operation that we are applying over here. So, we need to look at the block level also, that how those feedback elements can come into picture to determine the overall loop gain. So, this is giving you the open loop gain of the standalone amplifier. We need to incorporate the loop gain coming because of the feedback operation. So, let us go back to the block level description of our feedback amplifier. Again, I am reverting to the single ended topology just for simplicity of the analysis, and let me call this C1, C2, and you have the input signal over here. I am ignoring the large R for the AC operation. Now, here we have argued that this is a shunt topology, because you are mixing the feedback signal in shunt with the input signal, therefore, it must be current mixing, and therefore, I need to convert this input signal into an equivalent current source. Now, here we have C1 effectively providing you the Z1, and therefore, if we apply Thevenin's and we try to convert this into an equivalent current source, I need to use this C1 as the corresponding source impedance, or rather 1 upon SC1 as the corresponding source impedance, and therefore, the resulting current will be V in upon Z1, that means V in times SC1 is our resulting current source. So, I will make my current source as V in times SC1, and I will also put the impedance over here as 1 upon SC1. So, this is the input impedance, and then I have the C2 forming the feedback connection. Now, for the feedback circuit, if I look at the feedback configuration, this is shunt, and for opening the loop for a shunt configuration, this is my feedback network. This is the feedback element which is sensing the output voltage V out and providing the feedback current. So, let me draw one more step, let me complete one more step and then open the loop. So, here this C2 is sensing the VO and is providing us the feedback current IF, that is what we have seen earlier also, and therefore, we need to figure out the open loop circuit considering this shunt configuration. Now, in order to do that, this is our feedback network looking from the input port of the feedback network. Remember, this is the input port of the feedback network, because it is sensing the output voltage over here. The other terminal of the feedback network is having shunt connection, therefore, I will open circuit it, short circuit it while opening the C2. Therefore, in the equivalent open loop amplifier, I have 1 upon SC1, I have the V in times SC1. While opening this feedback loop, looking from the output side, this was shunt connection. For the shunt connection, we need to short circuit it. Therefore, I will put an impedance 1 upon SC2 over here from the output to the ground. So, whenever we are opening the loop for a shunt configuration, looking into the input port of the feedback network, other terminal is shunt, and therefore, we put a ground over there. So, we have 1 upon SC2 coming over here. Likewise, looking into the output port of the feedback network, this is the output port of the feedback network where you are having the IF going into the feedback network. The other end is once again shunt connection, we are sensing the output voltage, and as a result, we while looking into the output port, we put another ground over here, and as a result, we get 1 upon SC2 as the equivalent load impedance coming because of the feedback network. So, effectively we are arriving at the open loop equivalent circuit, and we are incorporating the loading effect of the feedback network on the main amplifier. Now, here if we look at this resulting open loop equivalent circuit, at the input port we have a combination of 1 upon SC1 and 1 upon SC2. If we look at the source, for the source this is acting like a parallel combination, and which one is larger. In order to get larger gain, what we have seen is we are giving 1 upon the C1 was supposed to be larger. Therefore, in the impedance, if you look at it, the overall capacitance or overall impedance over here, the 1 upon SC1 being larger is going to produce smaller impedance, whereas 1 upon SC2 is going to produce lower impedance. So, in terms of impedances, if I look at the complex impedance coming because of these two capacitor, the C1 is dominating, and therefore, we will assume this to be the dominant component. This may not play an important role with respect to C1, and therefore, if we look at the overall voltage signal developed at this point, for the open loop, we need to find out the overall A beta. For that, we first of all need to figure out the output voltage over here, and from there we need to find out what is the feedback current, that is the overall operation, right. So, the A, that is the open loop gain, basically the current to voltage gain multiplied by the feedback factor, which is the voltage to current conversion factor obtained by this feedback network, that is known to us. So, what is the voltage to current conversion factor, that is already known. What is that? This is the voltage. What is the IF produced by this feedback network by sensing this voltage? That is just VO upon the Z of this impedance, and that is just SC2. So, our beta is known, that is just SC2. Remember, in order to find out the feedback factor for the shunt case, we need to put a ground at the output port of the feedback network, apply a voltage signal over here, and then see what is the resulting current. Why do we put a ground at the shunt connection? Because remember, this is acting like a voltage to current converter. So, this feedback network is sensing voltage and providing you current. As a result, we are trying to estimate the gain, basically voltage to current conversion gain or voltage to current conversion factor for this voltage to current converter element. And whenever we are trying to characterize a voltage to current converter, let us call it a voltage to current converting amplifier, we need to put a short circuit at the output, because that is the best case for the voltage to current converter when you have 0 load at the output. Likewise, if you are finding out the voltage to voltage gain of a voltage to voltage amplifier or a voltage to voltage converter, the best case for a voltage to voltage converter is open circuit. So, when the voltage amplifier is not loaded by any external load, the overall gain is maximized. Therefore, for assessing the overall voltage to voltage conversion factor, we would open circuit the output port of the voltage to voltage converter, and likewise while assessing the conversion factor for a voltage to current converter like this feedback factor, we would short circuit the output node, so that the feedback network is not loaded by the amplifier. So, we are trying to characterize this feedback network, that given a voltage signal over here, what is the corresponding current provided by this feedback network. So, what is the voltage to current conversion factor for this feedback network for the shunt configuration. So, for that, while applying a output voltage at this input terminal of the feedback network, the other terminal will be grounded, and we will try to see what is the resulting current going into this feedback network, and therefore, we ground it and look at the current, and we get the factor SC2. So, that is the beta, and the remaining job is to get the A from here, the overall current to voltage gain from here, and for that we have to also note that the current by definition in this case is V in times SC1. This is the current that we have defined. So, if this is the current, we know that the voltage, as we are seeing, this is the dominant impedance 1 upon SC1, the smaller one, and as a result the voltage at this point is just going to be V in SC1 gets cancelled with 1 SC1, that is not going to come into picture. And then you have the overall gain, which is just given by the A of this amplifier. So, this amplifier is having some overall gain. We have just seen what is that gain of this amplifier overall, that is GMRO by 2 the whole square, that is the A of this amplifier, because this inherently this amplifier is the voltage to voltage amplifier. So, the gain from this 2 point to the output is anyway the A of this amplifier that we are using. So, that gives us V in times A as the final voltage over here. This is the final voltage, this is the V out, right. So, what is this is the V out, we need to find out V out upon I in. Therefore, what is V out upon I in? This is V in SC1. Therefore, the V out upon I in, that is the open loop gain of our current to voltage amplifier, is A upon SC1. This is clear, because effectively we are modeling this as a current to voltage amplifier. We are treating this as a current source. So, we are looking at the output voltage is V in SC1 multiplied by 1 upon SC1, that is V in only, V in times A, because this is our amplifier. So, V in is the signal appearing here times A, that gives us V in times A voltage over here, but that is the voltage. I want to get the voltage to current gain of this overall amplifier. Our current by definition in this case is V in SC1. We have arrived at the equivalent current source by Thevenin equivalent derivation. So, this is the V in SC1. So, we divide it and we get V out upon I in, which is A upon SC1, that is the open loop voltage to current gain of our shunt amplifier, and we need to multiply beta with this. So, in order to get the loop gain, which is, I would say, let us just name this loop gain, is equal to this times beta that we have already found out, that is going to give me A times C2 upon C1. So, this is the overall loop gain of the amplifier. Therefore, A times C2 upon C1, where my definitely my C2 is smaller than C1 in order to get larger gain. So, my overall loop gain is definitely smaller. I have A times C2 upon C1. In order to get a 100 gain, I would keep C2 to be 100 times smaller than C1. In order to get a 50 gain, I will keep this 100 times smaller than 50 times smaller than C1. So, as compared to the open loop gain, my loop gain is definitely smaller, and that will raise concerns regarding the precision and the accuracy that you want. So, here since the loop gain factor is smaller, we know that in order to get a good precision, we need to have the loop gain, that is your A beta of the overall amplifier, sufficiently larger than 1. If you want, say, 7-bit precision, we have discussed in the very beginning the precision requirement. So, if we are going for 7-bit precision, that means we want this overall loop gain A upon 1 plus A beta. So, A beta is what we have just found out, which is the loop gain given by A times C2 upon C1. Let me call this, do not mix these numbers. So, the A is the open loop gain. So, let me call this A naught and beta, A naught beta. So, this A is the amplifier's gain. So, let us not mix these two quantities. So, I am just considering the general case of a feedback amplifier where A naught beta is the loop gain we have just found out, and in that case it is, in our case it is A times C2 upon C1, where A is the gain of our fully differential amplifier 2-stage, and C2 upon C1 is giving us the ratio of the capacitors. Now, this to be much greater than 1, for 7-bit precision we would like this to be at least 100 times greater than 1. Why? Because if I take out these factors A naught beta, we are basically left with 1 upon A naught beta, and if A naught beta is much greater than 1, this is a small quantity, 1 upon 1 plus x, I can jump it up. So, this becomes 1 upon beta 1 minus 1 upon A naught beta, and in order to get a good precision, I would not like to depend upon this second term. I would like to be, my gain would like to be determined by only beta, not by the second term, because this term is highly parameter dependent, process dependent, and can change from time to time, can change from device to device. So, this is not a very precise component. So, I do not want to depend on this, and therefore, in order to get 1% precision, I would like this quantity to be less than 0.001, and that is the reason why I would like to have A naught beta much greater than 100. So, at least a value of 100 will be required to obtain a 7-bit precision or 1% precision. What we have seen is 1-bit precision means 7-bit accuracy for the digital domain, because if you are having 7-bit means you are trying to have 127 different levels in the data, close to 100. So, you want to record data with 100 levels of precision. So, therefore, you do not want even 1% of corruption in the data, otherwise higher 7 or even higher number of bits in the data is meaningless. So, in order to have 1% precision or close to 7-bit accuracy, I would like this quantity to be sufficiently higher than 100, at least around 100. So, that 1 upon A naught beta is less than 0.01, I am sorry, and that would mandate that this A naught is accordingly much larger. So, beta is chosen as 1 upon 100 to get a closed loop gain of around 100, that would imply A naught at least 10 to the power of 4. So, the open loop gain A naught of my differential amplifier that I am looking at will be at least 10 to the power of 4 or higher. So, that is the limitation which will be coming, because in this case my overall loop gain is diminished by this factor of C2 upon C1. Larger I try to get C2 upon C1, lower will be the A naught beta, and in order to get larger A naught beta, I would like to have larger A for this fully differential amplifier. That is one constraint we need to be aware of. So, now we have obtained the expression for the loop gain A naught beta, and next we need to look at the overall poles in our frequency response. So, in the open loop amplifier, we need to look at the critical nodes, and we have earlier also we have discussed that in this overall circuit we have the critical nodes coming at the output of the first differential stage and output of the second differential stage, and likewise we can look at the R equivalent of these 2 points and find out the poles, and we will follow the similar analysis. We will be looking at the overall frequency response coming from the 2 pole system and trying to look at the Miller compensation for getting an improved phase margin, and from there we will look at another concept of zero, how the application of Miller compensation creates additional problems, introduces zeros in the circuit, and then briefly we will discuss a couple of ways to address that issue and ensure overall stability for the differential feedback loop. So,
what is the typical value of open loop A?
A naught can be pretty large, means it depends upon your design. So, if you look at 180 nanometer technology, you can go to values of A which are even 10 to the power of 7, 10 to the power of 7 also possible, but for that you may need to use special techniques. So, there are some ways in which you can have very large gain without relying only on RO. So, we will study some techniques like gain boosting, where rather than relying only on RO, you can incorporate some additional components in form of amplifiers only in the main amplifier to boost the gain to very high values. So, high values are possible, but it adds more complexity. If you want to keep your design simple and if your precision requirements are relaxed, then probably 10 to the power of 4, 10 to the power of 5 is achievable with, without adding more complexity. But we will study some additional techniques also through which you can enhance the gain by orders of magnitude and go to 10 to the power of 7 gain also. Any other question? I hope the feedback operation is clear, how we are opening the loop and looking at the amplifier as a current to voltage converter, then finding out the current to voltage gain, and then multiplying it with the feedback factor beta to get the overall closed loop, overall A beta, that is the open loop response. That part should be clear. And only thing that we have to take note of is that we are using this amplifier overall as a voltage to voltage amplifier, but the feedback topology is a shunt. So, we are transforming the input signal into, or input source into, an equivalent current source, and then doing the rest of the analysis. After that, if you assume that this is the given source and this is the topology, from here this overall derivation should not be a problem. Only thing is initial step involved in transforming this input signal as a voltage to an input signal as a current.